Hello YouTube and welcome to What the Math. In today's video we're going to be talking about pulsars, and specifically we're going to do two things. One is we're going to talk about what they are and how they come to exist, and two is we're going to try to make one from scratch. So I'm going to show you how to make a pulsar and explain to you what they are. So these two are actually binary pulsars. This is a binary pulsar system. You can see their orbits. I'm going to actually disable them for a second. And these two have a name. They're called Taylor and Halsey? I'm not sure. In real life, I don't actually think they exist because normally pulsars don't have names. They usually have just number and letter designation, but I could be wrong. This could be like a new discovery that I've kind of missed. Anyway, so to get, if you do have the game, to get these two, it's actually a simulation right here. It's called binary pulsar. You can see that it's kind of beautiful. It's so unusual and so gorgeous. So it kind of looks like an eye. If you follow it, it sort of looks like an eye. Now, what is it? And is it real? Does it exist for reals? Or is this something that the designers of this game decided to just implement? Now, this is a real object. So these are actually neutron stars. And neutron stars, as you know, are very, 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 very dense leftovers from supernova. And these are specific neutron stars. These are neutron stars that actually, I'm going to accelerate this a little bit to real time. Let's make this real time. Okay, that's real time. See what's happening here? They're neutron stars that spin ridiculously fast, and I hope you don't have epilepsy because that was probably dangerous for you to watch. And so yeah, these are neutron stars that spin so fast that they start emitting these rays of electromagnetic radiation, which you see right here. Now, this is actually in real life would be invisible to normal vision, because this is actually X-rays or gamma rays. So you would need a special telescope. What am I talking about? That's not biology. Telescope that can actually detect really high energy radiation. So things like Hubble telescope can actually see this, and the beautiful thing about these is that they are actually very, very precise in their rotation. So if I were to actually accelerate this again, depending on the actual timing of its spin, it will always blink. I guess you could call it a blink at the same time over and over with very, very precise timing. So these are actually known to be so accurate that you can actually use them as an actual clock. So they're even more accurate than an atomic clock, which is probably the most accurate clock we have on Earth. So you can kind of call them lighthouses of space, because these are essentially sort of like location markers that show you exactly where you are in space based on their I guess how fast they spin and how fast they blink. So all of the pulsars that we know currently, they all have different timing. They all have anywhere from milliseconds to several seconds. So some of them blink every second, some of them might blink every 30 seconds, and some of them might actually do this several times a second. So they can have milliseconds spin. And because they're so precise and so accurate, you can actually find their location in space and use them as a kind of a location marker, which is something that astronomers have been trying to basically establish, so that we can one day use them as navigation markers if we ever start traveling across space and across the universe, because they're very precise and they're very stable. In terms of their life and so on, they can exist anywhere from 10 million to 100 million years, and some of them have actually existed for billions of years, depending on how fast they use up their energy. Now, what are these objects? Let's actually talk about their creation. Let's talk about how they're made and what they are. But before I do that, I remember in one of the previous videos I actually used Space Engine to kind of demonstrate that every neutron star has a kind of a light banding effect around it. So this is sort of like, this should be sort of, if you ever look at a black hole, it's sort of twisted and skewed. This should be like that as well, because these objects have ridiculously high gravity on their surface. You need approximately half of speed of light to escape from them, and some light may actually get stuck orbiting around them, so it may not even escape. And so what this means is that if you're looking at it, you will actually see nothing. You won't really see any light because they emit X-rays, and you'll see this like hole-ish looking thing that will bend the light around it. And if you were to actually step on the surface, the gravity would probably squish you, because it's so powerful. Actually, if you were to drop anything from like a meter high, so if you were to actually go on the surface, let's slow this down for a second. If you were to go on the surface of this, and we are on the surface right now, and you were to just stand here and drop something from 1 meter height to the surface, by the time it hits the surface, it would be traveling at 2,000 kilometers per second. And essentially, when it smashes toward the surface, it will probably just create a huge explosion or something. So that's how powerful the gravity field is here. And because it's called a neutron star, it actually contains nothing but neutrons. Neutrons are, if you know your subatomic particles, they're kind of like protons, same mass, but they don't have any charge, so they're neutral in charge. But nevertheless, this object does have electromagnetic charge, and usually from the energy that it accumulated and or absorbed from somewhere else. So if you look here, it currently has a very high magnetic field of approximately 5 million Tesla. That's a very high magnetic field, which is why it has this beautiful lighthouse-like effect. So this is what it's actually produced from. So magnetic field produces this. But the thing is, there's actually 3 types of different pulsars, and specifically there are pulsars that produce this effect because of the magnetic field. There are also pulsars, and these are called magnetars because of the magnetic field that they have. So these 2 are magnetars. But there are also pulsars that actually absorb various materials from, like, for example, if there's a star orbiting around them. Let's actually try to make that happen. If I were to put a star right next to them, just put sun here, very, very close to them. Can I put it that close? No, it's going to destroy them. Let's put it right here. Alright, that's good enough. So if there's a star right next to them, what they'll start doing is they'll start actually absorbing the sun's material, and they'll create this kind of accretion disk around them. So this is kind of the image that you've probably seen if you've ever looked at pictures of like black holes and so on. So the accretion disk will actually start accelerating so fast and create so much energy that this will also become X-rays and gamma rays. They'll actually start shooting out these really powerful rays. So that's another way of producing the pulsar. And there's also something called rotation powered pulsars, which basically as a neutron star starts to slow down, doesn't spin as much, the energy that it loses is emitted as X-rays and gamma rays. So that's another way of producing a pulsar. So, but the most popular ones are usually from the accretion disks or from the magnetic field around the neutron star. So let's actually, I'm gonna start from scratch, and we're gonna make one just from scratch, just so you can see how it's actually made and what happens when pulsars come to life. So we're gonna start with a star, and actually this is a new version of Universe Sandbox 2 right before the early access release, so they've kind of changed the layout a little bit, but I do like this more. So we're gonna pick a star, but something that's more massive. So we need to have something that's at least 8 times mass of Sun, because and I'll explain to you in a second why. Because we need that. Let's take, actually I'm going to take Betelgeuse, because Betelgeuse is awesome. It's fun to say it, and also it's fun to look at it. It's not too bright, it's not too dim, it's just perfect. Now this is a very, very large star. It has a radius of 4.4 astronomical units. If you know what astronomical unit is, it's basically distance from the Sun to Earth. So this is 4 times as far as Earth is from the Sun. Now, what we're going to do to this is, well, there's 2 ways of doing this. One is to basically just wait, billions of years until it goes through supernova and becomes a remnant. So we can do that. Or I'm going to cheat a little bit. I'm actually going to just start adding mass to it until it essentially goes into supernova. Now, what will happen to it after billions of years is there are 3 possibilities. One is if it doesn't have enough mass, like our Sun, for example, it will have a supernova, which is, of course, when you have a beautiful explosion full of colors. And then after the supernova, it will actually become a white dwarf. So this is what our Sun will become. It's something that's sort of bright, somewhat small, and will eventually, become nothing. or actually we'll just keep burning until there's nothing left to burn. The second variant or second possibility is if it's really massive, if it's actually more than 10, I guess, masses of sun. So if it's something like, for example, what has more mass than Betelgeuse? Let's find something that's more massive. For example, this guy right here, Spisa. I don't know how to pronounce this. I've never heard of that star before. So yes, this one here has 10 masses of sun, which means that if it after the supernova, after it actually goes through its life cycle, it will become a black hole. So black holes need to have at least 3 masses of sun after the supernova, so the leftover mass should be at least 3 masses of sun. If that sounds confusing, I'm going to explain to you what I mean by this as soon as I start adding mass to Betelgeuse. So let's actually decelerate this a little bit because we want to see everything happen in real life, in real time. And let's start adding, oh, okay. As soon as you add one little notch, it becomes a tiny Betelgeuse. Alright, so that's not cool. Let's try this again. Let's keep adding mass. It's going to grow a little bit. And here we go, nova remnant, and that's because this right here is a supernova. You can see it happening right in front of you guys. And so this was at 12.4 masses of sun, and the remnant will be a lot less massive. So because right now the supernova is going to throw out a huge amount of mass because of the explosion, so you can see if I accelerate this now, this is actually the mass escaping, and it's, the explosion, all this dust is actually just escaping. There's still going to be a remnant left, and this remnant is hopefully, if I calculated this correctly, yes, there we go, and it's a neutron star. Perfect. So if I zoom in on this, I'm gonna rename this now to Betelgeuse. How do you spell Betelgeuse? Pulsar, because we're going to be making this into Pulsar. Now, all of the stars, as you know, spin, or I hope you knew that, but they all spin. They all have a spin. They all have they rotate basically. Because this star was so large, it was spinning really slow. But if you take all this mass and then you combine this into a tiny point of only 12 kilometers, it will start spinning really fast. This is called momentum conservation. It's kind of like, imagine, you've probably seen this before, especially if you took physics class. If you have a skater spinning around and her hands extended, and then she puts her hands closer to her body and she starts spinning really fast. So this is what's happening here. Now this thing is going to be spinning ridiculously fast. If it doesn't spin, we're going to make it spin by cheating, and yeah, it's actually not really spinning that fast. Let's make it spin. So rotational period is going to be, let's just say 0.2. This is going to be 5, 3, 5. And then where's the rotational speed? I need to give it some speed as well. Velocity. Okay, let's say 2, 3, and 1. Okay, that will make it spin, right? There we go. See how it spins? Yeah, perfect. Actually, maybe a little bit too fast. I might have made it a little bit too fast. Let's make it slower. There we go. Okay, that's good. That's a good timing. Now, it also obviously will have some magnetic field, because usually stars have magnetic field, which means that we need to add, if it doesn't have any, yeah, it doesn't have any magnetic field, we're going to add, I just said 50,000 Tesla of magnetic field. I turned it to 5 Tesla. Oh, this was Gauss. Okay. Let's make it the same as those other pulsars. 5 million. 5 million Gauss. We're going to look at magnetic axes as well. So this is essentially, this is what's going to happen to Betelgeuse after it goes through its life cycle. Now, you can't really see anything right now because, there's all this material here and it's really bright. So we're going to accelerate time and wait for everything here to dissipate. We're going to just wait for it to dissipate and basically disappear. I think after like 1,000 years, no, 1,000,000 years, it's going to be all gone. So you can see time is shown here. This is 1 year, 2 years, 4 years. And the reason why you don't see the star spinning right now is because I accelerated time, so it's actually just, it's ignoring the spin because it's already spinning really fast. So, and we're just waiting for all of this extra solar cloud stuff to be gone forever, because we don't want it here. If you look closer, you'll see there's actually 2 axes. There's a axis of rotation and axis of magnetic field. Just like on Earth, they don't have to align together. Magnetic field can actually have its own axis from the axis of rotation. But in this case, they're pretty close together. So here we go. Excellent. Okay, it's all gone after 35,000 years. Let's decelerate to seconds. Try to make it as close to reality as possible. 1 second per second if possible. And here we go. Alright, now look at this. Awesome. It's already kind of spinning. And it's giving us this beautiful, awesome looking thingy of that looks like an eye. So essentially we just turn it into a pulsar. Now it doesn't spin as fast, so you can, if you want your pulsar to spin faster, you can either basically start with a star that's spinning faster, so when it becomes a neutron star it has a bit of a more spin. But I'm just going to do this manually by adding go to motion, and right here we're going to add, where is it? There it is, rotational period. So I'm going to change this to maybe, just say, I'm going to change it to 0, 1. Change this to 1. Here we go. Excellent. So this is an actual real-time rotation. Now it doesn't actually look as beautiful as it can yet, but it's getting there. We're gonna make it wobble as well. So we're gonna change its rotational velocity around its y-axis. And here we go. This is the flippy floppy pulsar, as I call it. This is a scientific term that I just invented a second ago. What I mean by this is that it actually rotates and flips on its own axis, kind of like this, so that and then it pulsates every few milliseconds. I think this is actually a very, very fast pulsar. It's decelerated right now. If I actually have real-time acceleration, it does this blinking, I think, several times per second. Something like maybe 20 times per second, which is actually, they do exist in real life. There are some pulsars that are really, really fast. Now to do this, if you want to actually do it this way and not just vertical spin way, you have to change the magnetic pole angle. I was actually looking at the wrong thing. If I change this to 0, it becomes just a regular, spinning pulsar. It kind of looks like, more like a black hole, I guess. And if you want to make it into a flippy floppy one, you just have to change this to, let's just say, 50 degrees. And there you go. So this is how you make pulsars from scratch in this beautiful game called Universe Sandbox 2. Now, one thing I forgot to mention about pulsars is that, well, yes, they're very, very, very dense. They're also very, very, very massive. And some of them live very short time, only about 10 million years. So they'll actually just stop producing X-rays and eventually just, extinguish themselves. Or at least that's what we think happens. But some of them live for billions of years, and those are the ones that don't actually emit that much energy. And some things I haven't actually mentioned about the pulsars and neutron stars yet are that they actually are responsible for some of the more beautiful elements of our night sky. So there's one right here. This is actually called the Hand of God. And this is one of the most beautiful things you can actually see in the night sky. And right in the middle there, the white part is actually a pulsar. So there's quite a lot of them in the sky. They're they're all over the place. Like I said before, we know about 2,000 actual pulsars in our vicinity, and there's probably like billions of them in our actual galaxy. And a lot of them have already been extinguished because they've lost their energy and their power, but a lot of them are still around. And essentially what these are, once again, are super, super dense leftovers or remains of a star after it undergoes a supernova, and specifically a star that's not really that massive to become a black hole, but also not very light to become a white dwarf, so somewhere in between the supermassive stars and not so massive stars. And most stars are actually spinning, so they will usually become pulsars, not just neutron stars, but also pulsars. And the thing is, these are the only neutron stars we can actually see. If the neutron star is not spinning, and if it's not really doing anything else, it's kind of impossible to see it because they're so tiny and they don't really produce enough energy for us to detect them. So yes, pulsars are the neutron stars that we know of and that are all over the place. These are awesome, they're beautiful, and this is how you make them in this game. And just for fun, before I finish this video, what I'm going to do is I'm going to try to make a binary pulsar. by introducing yet another star in here. Let's actually put another Betelgeuse because we know it works. And what we're going to do with this, oh no, it's going to destroy my beautiful, is it going to destroy it? Let's see what happens actually, let's see what happens. We're gonna put it right here, and I'm gonna just make it smaller, there we go. And now let's make it into, there we go, excellent. I think it has supernovaed. So now all I have to do is just wait for the supernova to disappear, so that we can then create yet another pulsar and make this into a binary pulsar. Now, the way binary pulsars are made is usually from two massive stars that orbit around each other, and usually the more massive ones will actually supernova first, just like in this case it was this one. Then it will siphon off some of the materials from the less massive star, and once the less massive star, once it's kind of prepared itself for a supernova, two things can happen. One is maybe it will explode and destroy the entire star system, so that both the old neutron star and the new neutron star will just fly apart, or possibly they'll remain in the same orbit and they'll create a binary pulsar system, which I'm going to try to create right now. So we need to wait. Wait, did my other neutron star fly away? I have a feeling it flew away. Oh no, it's all gone. Oh no. Oh, there it is. There it is. Don't fly away. Don't fly away. Come back. Come back. No, come back. Come back to me. Oh no. My pulsar. My Betelgeuse pulsar. Okay, so yes, it just so happens that it did fly away, which is kind of realistic. I mean, this could happen if this second star actually supernovas, its explosion may dislodge the neutron star and it will just fly away into outer space. I'm gonna try to see if I can rebalance this. Can I actually rebalance them? Can I put them together in an orbit? And there we go. So we have two Betelgeuses that have become neutron stars and are now pulsars, pulsating and orbiting around one another. Actually, I'm not sure if they're orbiting. I know they're actually close to each other, but they might not have an orbit, so they might actually collapse into each other. But yes, this is how Betelgeuse will one day become a neutron star and possibly a pulsar, and this is how neutron stars are made. One thing I forgot to mention, there's also in materials there's a button here that says particle jets. This is actually, you can also show aurora belt, but it's not going to really show you anything. But what this does is this: it turns the pulsars into actual particle projectors, kind of. It doesn't look as cool though, but this is essentially just to give you an idea that this is what we detect on Earth. So we detect these pulses that you see projecting. So if I slow this down, we detect these pulses, which basically are created by the rotating pulsar. So I'm going to disable this because this doesn't look as cool. This is just a more of a mathematical approach to counting how many pulses you get per second. But this is essentially what it looks like, and this is a perfectly balanced handmade pulsar binary system. Let's actually accelerate a little bit and see what happens, because I'm not sure if they might actually smack into one another. Oh no! Oh, here we go. Oh no, they're flying apart. All right, so that works too. So that's basically the essentials and the basics of pulsar. This is how they work, and this is what they are. Pulsing neutron stars. Hopefully this was fun and clear, and hopefully you enjoyed this video. If you did, check out some of the other Universe Sandbox 2 videos I posted before. And if you have any suggestions for any other games I should try and take a look at, please post them in the comments below. So this has been What the Math with Universe Sandbox 2. And just a reminder, the game is about to hit early access on Steam, so if you don't have the game yet, it's probably best to get it soon, because it might actually go up in price and will be more expensive once it's on early access. And hopefully it will actually also hit final release sometimes next year. Anyway, thank you for watching guys, and game you later. Bye bye.